we used an entropy energy argument, which is very similar to kind of the Peierls argument that we've seen several times, to argue that there's a temperature, like a crossover temperature, in the free energy that signals when free vortices start to appear, which you saw in the simulations. You know, below the Kosterlitz-Sallis transition, where n squared is the charge, the topological charge of the vortex, you basically have no vortices, or as we're going to see today, they are actually vortices bound with a logarithmic Coulomb potential. And above that temperature, they can unbind the plus and minus vortices. And I'll use this TKT throughout today's class, and lots of times I'll be assuming n equals 1, or n equals +1 and -1, for a vortex that's created as a vortex-anti-vortex pair, which, remember, look like, so n equals 1, n equals -1, with field lines, it would look like this. So down, up, something like that. So that would be a vortex-anti-vortex pair. Okay, and below, so, okay, above first is easier. Above TKT, we expect a proliferation of vortices. And these things kill all the long wavelength fluctuations, like the long wavelength spin waves, if you want to call them that, which we considered in the treatment of the nonlinear sigma model. So remember, this is sort of outside that long wavelength treatment. So the system's is a paramagnetic phase with an exponentially decaying correlation function, g of x, g of r. Whatever, there's a correlation length, so it would just say it's r over just the usual paramagnetic phase. Whereas below the Kosterlitz-Sallis transition, so we call this quasi-long range order. Because it's critical in some sense. And the two-point function looks something like, oops, r. So it's d. Remember, the exponent on this is, I think it's a d minus 2 plus eta, and we're always in 2 dimensions. This is like the O2 2d. So we just have an eta. And I calculated this last time. In that Gaussian integral that I botched, but it's t over 2 pi j, where j is the coupling in front of the Hamiltonian. So that's sort of your anomalous dimension. So you can note that if you put in plus or minus 1 for the vorticity, then, you know, at the transition temperature, you can just substitute in the Kosterlitz-Sallis temperature, and you'll see that eta is a quarter. So you get a large, you know, even from this very simple theory, you get a large anomalous dimension. The anomalous dimension is usually 0. It's 0 in the Gaussian theory. So here it's something appreciable. This is often sort of the easiest check that you can do to see if a system's in, or, you know, if a certain phase transition is of Kosterlitz-Sallis type. Because it's such a strong signal, you know. So. So I'm going to talk about the binding potential of a vortex and an anti-vortex. But before that, let's just talk a little bit about sort of experiments. I mentioned helium in the context of the ON model. So that would be the 3D O2 model. Kosterlitz-Thouless transitions in 2 dimensions are also, prototypically seen in helium. So let me talk a little bit about that, because in that case, the vortices, they correspond to, vortices in some sort of mass flow in the superfluid fraction of helium. And the experimental signature that is used to detect a Kosterlitz-Thouless transition in helium is the same one that we use numerically, say, in Monte Carlo simulations. So in your computational project, which I don't have on me, you're measuring a stiffness. And that stiffness is the same stiffness that's measured basically experimentally. And the signature in the stiffness is a jump called the Nelson-Kosterlitz jump. Nelson-Kosterlitz. Or discontinuity. So in helium, let's think of the experimental context instead of the numerical one. So what is, I always told you the O2 was the phase of the wave function, right? So in these types of experiments, you can do a simple semi-classical derivation of this Nelson-Kosterlitz jump. So nothing's going to be very rigorous here. We're just thinking of, helium with a complex wave function. Psi with an amplitude and a phase. Let's see. And we don't care about time dependence here, so it's just IKX. And let's write this in terms of momentum. That's kind of the semi-classical way. And then we'll write that momentum as a velocity. And we'll relate the velocity to these field lines, basically this variable theta. So there's a complication in helium in that it adheres to a 2-fluid model. So only part of helium goes superfluid. So only part of helium basically will, only a small fraction of the total density will undergo the Kosterlitz-Thouless transition. So let's just keep that in mind. There's a superfluid fraction. And we'll just say, in the usual semi-classical way, we can define a velocity from this k vector, writing my wave function like this, so that I can relate the argument of the exponential to just some phase. And this is kind of a 1D sketch. So generally, then we can define that velocity here as this numerical prefactor times the gradient of that phase, right? So in 1D, when I take the derivative with respect to x, I'm left with the velocity up to some factor. So for, let's say, theta r, because we need it in 2D, right? Then I'll say v h bar over m is grad theta. So we'll use that more and more. And from this, we can define a kinetic energy, which will be the energy of the superfluid, the energy of the superfluid helium. So kinetic energy, 1/2 mv squared, but we need to allow for, positional dependence of this velocity, essentially. So we're going to write it as an integral. So that's the kinetic energy. So I'm going to define, so it's 1/2. I'm going to define a mass density, rho s, and then an integral, right? And so remember, okay, so it's v, so I need an integral of v squared, and then say over the two-dimensional area. So it's per unit area, so I'll call it superfluid. Yeah, for the units to work out, it's per unit area, so super. Right. Okay, so again, roughly, just sort of semi-classically, we substitute in my expression for V. So it's rho s squared. Right, there you go. So that's the derivation of the XY model, if you will, semi-classically for that phase of the complex wave function. And the only difference is I had a coupling in front of the XY model, J. So it's rho s, and then this h bar over m. So m is just the mass of the, say, helium atom. So, except for this case where you care about the experiment, we just always set this equal to 1, and then J is equal to this, superfluid density. So that's it. So then we can calculate the ratio of the superfluid density to temperature as we approach the Kosterlitz-Sallis transition. So strictly at TKT. So that gives us the universal jump. Two over pi, right? 2 over pi, and all those masses, and h bars that nobody cares about. So this is important because this is what's measured experimentally. And it's called the Nelson-Kosterlitz jump, so this is not a rigorous derivation. But a rigorous derivation gives you the same thing. So above the Kosterlitz-Sallis temperature, basically there's no superfluidity. So the superfluid density is 0. So that's why it's a jump. So it looks like rho s t, tkt, and you're moving along here. There's a jump. And if you plotted the line, you know rho s is equal to 2 over pi t times that constant. Then that's the value. So the intersection of your superfluid density with that line is the value of Kosterlitz-Sallis. Why? I mean, it's redundant, but what happens experimentally and also numerically is you don't quite see like a discontinuity. So experimentally what happens is they use torsional oscillators. So Bishop and Reppe did this first. Bishop and Reppe. Why, I think. So they used a torsional oscillator, and they absorbed helium in thin films on mylar. So that gave them a two-dimensional film. So what happens is you put, they stack these mylar films in a torsional oscillator, which rotates, back and forth. It's driven at a certain frequency. And then you cool the system down. And as you cool through the Kosterlitz-Sallis temperature, you lose some of your moment of inertia of the oscillator. So because the superfluid velocity, the superfluid velocity fraction is grad theta, then the curl is 0. Right? So and because of that, part of your flow becomes irrotational. In that velocity. And the torsional oscillator basically has a moment of inertia. And you see this moment of inertia as a function of temperature. Jump from the classical value. So I classical. So 1 minus rho s over rho. So the superfluid fraction, when it turns on, can be directly measured in the torsional oscillator. What happens is because it's a dynamical system, you're measuring a response function. You actually get a curve that has some sort of dissipation effect. So this is from. And so this universal jump tells you precisely where Kosterlitz-Sallis is. It's the same for if you do this numerically. If you do this numerically, you'll get a finite size effect. So you'll get a continuous curve. And for different finite sizes, the point where each finite size curves intersects this line is basically your finite size estimate for the Kosterlitz-Sallis transition. So numerically and experimentally, things look very similar. So if you choose to do that project in your computational assignment, I forget which option it is, what I have you measuring there is rho s, which has some microscopic, estimator that has to do with the topological winding numbers of all the vortex lines. Sometimes it's called the spin stiffness. Okay, so that's just a bit of phenomenology. Like I say, this was measured in the late 70s. And at that time, they actually had the full theory for the dissipation. So you can look at that Bishop and Reppe paper, and it's still pretty interesting to this day, I'd say. Questions on that? Incidentally, these torsional oscillators are what people have been using to try to search for supersolids. So they take bulk helium, put it under pressure, and then it forms a crystalline state. They do these torsional oscillator experiments, and they look for this non-classical moment of inertia. And there was claims in 2004, 2005, that people were seeing super solid solidity in bulk helium. And it's been pretty controversial. So I think those experiments, they're sort of sensitive. They've been sort of debunked. And just this year, people have now seen super solids in cold atoms. So this type of torsional oscillator experiment it's pretty important. They're pretty important historically. Anyway, that was just a comment. I want to calculate the Coulomb potential for separation of the vortex-anti-vortex pair. And this justifies, I think, in part, the idea that we have a binding or an unbinding transition. So below the Kosterlitz-Sallis transition, a single vortex has this logarithmic energy, log L over A, where L is the system size. Because you basically got to create this defect that goes from the vortex core all the way out to the edge of the system. So you get rid of that logarithmic cost in the energy by taking a vortex and anti-vortex, and then basically using the anti-vortex to gobble up that string until they're very close together. But as you saw in that numerical simulation, you also do get sort of finite range pairs of vortex and anti-vortex pairs, even below the Kosterlitz-Sallis transition. Okay, so let's derive that sort of energetic function now. So we're still sticking with the XY model. And all we have is the usual action and this idea of vortices. And what I'm doing is I'm relating this to a neutral Coulomb gas. So it's just an analogy. Okay, let's start from our definition of a vortex. Simplest case, n equals 1. If I take a contour integral anywhere such that the core is inside the path, then 2 pi n. And I'm going to use this definition of a velocity. Sometimes it's just called a distortion field. And I'm going to set h bar and m equal to 1. Okay, so just like the velocity field for a massive superfluid, say. So then let's just apply Stokes' theorem. Okay, so what does that mean? So that's V. I have X and Y. So my area element, right, which is what this is, has an orientation. And so I'll call that direction Z. So let me just do it like this, Z. And then I have to have a Z component of the curl. Right, so that's it. And this thing is going to equal 2 pi n. So this is 0 in some sense, like I said over there, but really what it means more rigorously is the Z component of the curl is a delta function, right? Centered at the origin of that vortex. So this implies the Z component is 2 pi, maybe n. And just, for more than one vortex of different charges, I think it's fair to say I can just sum up contributions. So 2 pi. So I got to label my n with ni. And then I need a delta function. But now I can't put my coordinate system's origin at the, at every single vortex center, right? So I need a delta function that cares about, let's see, r minus ri, say. Okay, so that's for many vortices. Okay, so remember the vortex is, so I'm in a polar coordinate system, but I want to change to a Cartesian coordinate system to calculate this curl. Because the z components are like, partial y minus partial x or something like that. So in polar coordinates, I have a angle, I call it phi. And then theta was just equal to n phi. And I have a unit vector, phi hat. And let me just stick with I'm just going to get confused with that n everywhere. So what I need is the derivatives, because I have my v, right? So I need components vx and vy. Right. And my theta is just defined as, arcs. Okay, so the Cartesian coordinates are r cos theta, r cos phi in that coordinate system. And y is r cos, sine. Okay, so we've done this many times, but it's always confusing. So if I solve for theta, and take the derivative, then I'll get v of x is minus y over r squared. And this one is x over r squared. Cool. So that lets me calculate the curl. So I just introduced v, which is the distortion field or the velocity. But you can actually simplify things by making a slightly different substitution. And this is called a stream function. And I'm going to use psi, but it's not the same size as the wave function. So this is satisfied. These are satisfied. It's just sort of like the velocity in a different coordinate system. I could have came up with another symbol, but too late. So it's going to be a log. So if I have log of r, but I have this defined up to a constant of integration. So I'm just going to plug that into the log. Call it r naught. Then vx. So this is the y part. So it's a partial of the stream with respect to y. And vy, which is this one, should be the minus, I think. Yeah, minus with respect to x. Okay, that's just it's sort of just a mathematical mechanism, but it's going to be useful. Okay, good. So that's for 1. I just did that for n equals 1. But I need this more generally for many vortices. Okay, so more generally, that function will be, so it's minus, it's a sum over all vortices. They're topological charges. And we're in a different coordinate system, so it's r minus ri over r naught. Okay, that should be enough. Okay, so I have this thing. So let me calculate now this thing here. Okay, and I'm just going to plug it into the basically energy equation. Okay, so this is V, so by definition it's V. So it's in the Z direction, so it's this minus, oh no, X partial Y. Right. And the reason we introduced this stream function, okay, so now I have V's. I know how V's are defined in terms of partials of theta, so I can write this as second derivatives of the stream like this. Oops. And because of the signs, this is going to work out nicely. This is just like del squared, the Laplacian. Okay, so now this lets me calculate my energy. And I'll just use the XY model, which is J over 2 dx dy, this thing, which is like, you know, V x squared plus Vy squared. So what this gives me is like the, you know, derivatives of, or the gradient of the stream function. So it looks like a gradient, it looks like the same form, but in the gradient of the stream function. And so that's the point. They're not, psi is not equal to theta, but the way it's defined such that the signs work out, so that the energy is equivalently equal to say this. And there's one more step here where you can take it, you can integrate by parts. You know, so you have the integral of derivatives. It's annoying, I'll just write down the answer. You always pick up a minus sign. So it's this thing times the Laplacian, that's what it is. D squared x. Okay. So I know what psi is, and I know what this is in terms of this equation here. So now I just put it all together. if this works. Okay, so let me write what I'm doing here. So I'll just rewrite it. So since no Ri and this thing is what? Minus 2 pi sum over I and I R minus Ri from this. Then my energy, you'll pull this 2 pi out. Dx, dy. Gotta be careful with my sums here. So I'll call the second one J. Okay, so I have a 2D delta function. This should probably have been labeled a 2 there. Okay, so that'll take my R, and make it Rj minus Ri. And I still have 2 sums. And the only thing I have to be careful of in those 2 sums is that, if both, what is it? If both vortices are all, I and J occur at exactly the same spatial position, then I got to worry about this, this log of 0. So we'll just assume that doesn't happen, or we'll just enforce it by making I not equal to J, Ni and J log whatever order you want here. And, as always, there's a core energy, E core for, I don't know, for all the vortex cores. Which doesn't bother you if you're on a lattice. So the way you interpret this is below the Costas-Salas temperature, you can imagine starting in the completely uniform state that might have long wavelength fluctuations. Those are in principle handled by the long wavelength theory. But in order to get over the logarithmic and L energy cost of a single vortex, you'll create vortices in plus-minus pairs. So you'll basically have a +1 and a -1 here. And for each of those pairs, you have an energy cost that's logarithmic in their separation distance, right? So that energy is minimized when those 2 cores are close to each other. And that's the Coulomb potential. That's the neutral Coulomb gas. Right, because log R, that's why it's called that. So. And I say times Nj is less than 0, whatever that pair is. So it's like a binding potential. They're bound together. So you call this it's the equivalent of a dielectric. And above the Kosterlitz temperature, you know, the entropy wins. You don't care about the Coulomb binding potential anymore. So thermal fluctuations, I guess you can call it melt. Let's call it melt. So this is like a vortex plasma. So two-dimensional Coulomb gas. That's the analogy. Questions on this? Makes sense?
So like between going second and third line of the platform.
Okay.
Integration by parts.
You talking about here?
Yeah. Like why before there was Vx, or like the label of. Yeah.
It's all just the area element. Yeah. Call it DR.
But I'm just looking for. Because like it looks like you're considering like the energy of each singularity separately, and then somehow they get mixed up, right? Like two of them start interacting.
From the delta function, so you have a term. When you do this, when you integrate by parts, you have this delta function, which when you take that integral makes R equal to RJ.
Right.
So it's important to include this delta function here when you first motivate the curl.
But without that, like, what's the motivation to do this integration part? Like, if you would have inserted the expressions for.
Well, you would still have a square here,
yeah.
So you still have two sums.
Right.
So you just got to keep those sums separate, and then you have these two sums, you know, and this is the way. I mean, this is just one way of. You can also have two sums here. But I don't think you can solve it in one line then. So it just has to do with the fact that you have this quadratic energy. And there's corrections on this, of course. So that really motivates, I think, like, you know, these are all pieces of some physical puzzle where you have, you know, at zero temperature, you would have a strictly ordered ferromagnet. You know, everything's aligned in one direction. Whatever in the plane. And for, you know, T, I don't know, very small, or T over J, right? Then you might get long wavelength fluctuations. I don't know what they look like. Which strictly kill the long-range order. So there's no long-range order here. That's Mermin-Wagner theorem. But then you can also get bound vortex, anti-vortex pairs. as long as they're close together. And then for T greater than the Kosterlitz-Sallis temperature, so again, you don't have any order parameter here. What you have is a stiffness, like that rho S. That's another story. And then above the Kosterlitz-Sallis temperature, these vortices entropically just want to live by themselves. And so you just have vortices everywhere in the system, of all sorts of ends. Hence, that's like your plasma. So the number of vortices in the system basically determines, in some sense, whether or not you're ordered or disordered. And that number, if you're thinking of an RG sense, if that number of vortices was a relevant variable, then that would indicate that your flows are going to the paramagnet. And if that number of vortices is essentially constrained by this Coulomb potential, so if it was irrelevant, then you can imagine staying in the quasi-long-range ordered algebraic decay phase below the Kosterlitz-Sallis transition. So that really rough intuition, let's use that to, I hate to say derive, but to motivate the Kosterlitz RG equations. So in your assignment 5, I've given you, these are sort of generalized, but I've given you recursion relations in temperature and some other variable that I've called the fugacity. And the fugacity is the number of vortices in the system. So let's motivate those equations now. I can never derive them in the amount of time I have left. So I'm just going to do the sketchiest derivation that you've ever seen. But there's 2 ingredients, and we're just motivating it in the same way that we have derived these momentum shell RG in some sense. But we want relevant variables. So temperature is 1, obviously. So we need a relevant variable that looks like the difference from the Kosterlitz-Sallis temperature. But what I'm claiming is we also want another one that's somehow related to the number of vortices in the system. And the question we want to answer with the RG is whether or not that number of vortices is relevant or irrelevant. Okay, so this will give us basically the RG equations in problem 2 in your homework 5. Okay, so again, I want two equations. One in, T? One in temperature, which tells me somehow the distance I am from the transition, and one in this variable y that I've defined on your assignment. So start with I'm going to set n equals to 1 everywhere. And so let me just imagine constructing a relevant scaling variable somehow that measures the distance from the Kosterlitz-Sallis transition to, so let me pi j. Okay. So x vanishes at the fixed point. Okay, so I have one scaling variable. It's like T minus TC. Basically, it's taking the role of that. And I need another one that's the number of, that somehow tracks the number of vortices. And that number, again, somehow proliferates above the transition. Okay. So if there's few vortices, which one is that? So then it's like the long wavelength physics is fine. So Mermin-Wagner, spin waves. Whatever. And if there's many, then the vortices destroy all that long wavelength spin physics. So if under an RG step, whatever this variable is relevant, then I'm going to be flowing to the paramagnetic phase. That's what the plasma is. Paramagnet. So unlike the Ising model, I don't have something like a field that I can couple directly to the degree of freedom, right? I mean, I can couple a field to the spin, h dot theta, but what that'll do is it'll just order me into this, trivial ferromagnetic phase with a strong enough field. So a magnetic field isn't the right, it's not the right variable, but it's the right idea. So what a ferromagnetic, what a magnetic field does is somehow, promote in the Ising model, spins to a line. So I need something that promotes, vortices to either appear or disappear. And, we'll use just, a chemical potential for that. So it's very similar, a field and a chemical potential, but the chemical potential is the thing that tells you whether or not there's a cost in the partition function for a number of vortices. So it's like we're in the grand canonical ensemble for the vortices. And there's no physical field, there's no physical knob, like experimental knob that directly kind of gives you this chemical potential. Okay, so that's kind of unsatisfying in a way, but who cares? It's just a mathematical construct in some sense. And so from this, we're going to define a fugacity. And that is just, the exponentiated chemical potential that would occur, say, in the partition function. Okay, so I'm going to call it y. Why not? E to the minus. Let's see, I want mu. Yeah, I can put a beta there. Beta mu. I don't know what sign. Depends on your chemical potential. So, okay, so small fugacity, if I have this sign, is large U. Okay, and mu. And large mu means large chemical potential, so large number of vortices. Okay. Small y, large. No, this is few vortices. Yeah. And why don't I? Oh, I did the small. Oh yeah, small. So then large, fugacity, small potential, right? So and that's the paramagnet. Yeah, okay, that's right. So if I'm flowing to, if my RG flows to large Y by this definition, or Y naught, then that's going to be the trivial paramagnetic phase. And that's what we're interested in, whether or not, that's the big question. Does Y naught increase or decrease along RG flows for an RG step? So let's consider the case where I have basically that Coulomb potential, and I just have a vortex-antivortex pair. Okay, so I know what the energy is, and I'll use this to define a probability of introducing, say, a vortex pair into the system. So let me just restrict that sum to one pair. And n, I don't know, 1 equals 1, and n2 equals minus 1. Right. So my energy is logarithmic in their separation. Plus 2 cores, whatever that is. So I'm imagining a grand canonical ensemble of vortices. Why not? So I can define essentially a Boltzmann probability, which is e to the minus beta e, maybe e to the minus beta mu. Okay, so that's just a pair of vortices, a probability. Statistically, I don't know. I'll call P N1, N2. Okay, so there's 2 fugacities. There's 2 vortices. I'm probably going to lose track of this factor of 2 somehow. So I have y naught squared from this. And then I got 2 cores. Minus 2 beta e core. So there's no positional dependence in any of those parts. And then I have that logarithm, which I'm exponentiating. So it's R1 minus R2, R naught, raised to, I got 2 pi j out front, and I got a beta. So it's minus 2 pi j over t. So there's a positional dependence in this probability. So, okay, here's where the sketchy part comes in. But it's fun nonetheless. So I'm basically creating this vortex-antivortex pair. There's a probability depending on its distance. So if I create them at different distances, my probability goes down in some sense. So if I measure the 2-point function, right, in the distribution, I have to take the trace and everything. But, because, once I do that trace, I'll find the same, positional dependence as the probability. So that's not obvious maybe, but you would have to do the trace to do it. So it's just very rough. So P is proportional to, say, the 2-point function defined in some way, which I'm not going to actually care too much about. All I care about is the scaling dependence. I'm going to think of that 2-point function as going as 1 over, so it depends on the separation distance, say. So it's like C R1 minus R2. And I'll imagine it going as 1 over the distance, separation distance R. I think it's 2 minus D, or is it D minus 2? I forget. Let's see. Whatever it is, D is equal to 2 plus eta. So it's 1 over R to the anomalous dimension. And I'm going to relate the scaling dimension that's contained within eta to the scaling dimension of that field X, which gives me the spatial dependence. Okay, so this is the rough thing that I can do in 5 minutes, which isn't actually very rigorous. Okay, so this implies, oh yeah, I have it right here. So here's my R. All right, so then that relates my eta to the argument of that probability, or that 2-point function. And since when we did the scaling arguments, we said eta is equal to D, which is again 2, minus 2 times some scaling dimension. I'm going to do something bad here. I'll get back to what this is. I just realized this terrible notation. And I think I need a 2 here. So it's 2Vx, where I've defined. So if I have my scaling variable, after an iteration of the RG, I just realized that's the same as my velocity field that I used earlier. Not the velocity. I usually call these either X or Y, but now I'm using X or Y everywhere. Anyway, I could have thought that out better. So then, the scaling dimension V for that variable is pi j over t. Yeah, sure, why not? Don't repeat that derivation to your mother. That was not something that you will get any marks for on an assignment. But that's the right answer. Turns out to be the right answer. Probably coincidentally. So now I need the same scaling dimension for y to know whether it's relevant or irrelevant, right? So, and again, I'm calling those things v's. So I need v of y. And that's distance independent. That's a distance independent part. So I'd say y prime is b to the vy y. And I'm going to group things together here. So, because I have a core energy Yeah, so I have y naught squared, and I have e to the minus 2 beta e core. So I can define y is just y naught e to the minus beta e core. And I'm just sort of absorbed in that other part that doesn't matter. So I need v of y. Okay, so here's another sketchy derivation. So think back to that single particle energy, or sorry, single vortex energy, which had the logarithmic dependence. I mean, it's like the simple version of the Coulomb potential. So it's from last class, but it's what we argued was the energy entropy balance. Okay, and L is your system size, right? So somehow the fact that the core is topological, or the vortex is topological, affects your energy in some sense. I'm dragging around this E core, right? So then beta times this thing, which I'm going to put in my exponential, is pi. Why do I have a j squared? It's only a j. So it should be j n squared over t ln Okay, so let's think of the grand canonical partition function for one core. So I have Z. I have a sum. Over all the possible ways that this core can be put into the system. And if it's a two-dimensional system, I only have one core, it's going everywhere, so that sum just turns into all the possible core positions. And then I've exponentiated arguments, so it's only one core. So, okay, so I have one chemical potential, I have one energy, and then it says all possible vortex core locations. In an L by L lattice. Okay, so this is sort of unphysical. Okay, so I have something that looks like my fugacity that I can pull out front. So that's the point. So I have, I'll call it y naught from this, and then e to the minus beta e core. So that's actually my y. Then I have L over A here and here. So 2 minus pi j by t, and I'm dragging around this n. That's funny. So that's like your y of A, say. You know, you can imagine it before the RG step. So what you would do is you would take A to B times A, right? And define your lengths in terms of that. So then y, I'm just going to use y. B, A is, right? And the B gives you 2 minus pi j over t n squared there. Okay, I'm done with this n squared. And then I have y of A here. That's where the scaling dimension is, again, very roughly, right? So I've just written the partition function in the roughest approximation for a single core, and look how it scales under a single RG step. So that's, by definition, y prime equals b to the v y, y. And so it's 2 minus vx. Well, I can't believe that worked. So with my usual trick, then I can derive the differential RG equations in various ways. And one way to write it is just by putting x back in. So now I have the differential RG recursion relation in terms of x and y. And that's actually right, despite this. That's the correct RG equation. So that will tell you relevance and irrelevance of the fugacity. And it'll tell it to you as basically a function of x, which is invented to tell you whether or not you're above or below the Kosterlitz-Sallis transition. So it's, at high temperatures, y is irrelevant because of the sign of this term. And at low temperatures, y is, no, I got that backwards. It's relevant at high temperatures and irrelevant at low temperatures. And for that to make sense, this is one RG equation. We need another RG for, the temperature somehow. So the temperature is in this equation. I'm not going to derive the other equation. I'm just going to say that if you imagine, okay, so if all the temperature dependence is here, in terms of the relevance or irrelevance of the Kosterlitz-Sallis, the distance from KT, then the other equation should just depend in some order on y. And if you expand things out to lowest order, then the lowest order, because you have to create vortex and anti-vortex pairs together, should be y squared. So it will depend to lowest order on y squared only. So who cares about anything else? So for convenience, 4 pi cubed y squared with higher order terms, and dy dl is what? 2 minus pi j over t y. So if you look in your assignment 5, those are the equations that you're fooling around with an additional epsilon dependence. So the first equation gets T, gets modified in temperature up to epsilon. Okay, but that's sort of like saying you're going away from 2 dimensions. So these are the strictly 2-dimensional O2 RG equations that come from Kosterlitz-Sallis.
And where is J in the assignment range? J
Probably set to 1.
and 1.
Yep. Because who needs it, right? All it's doing is, I mean, you don't have any other parameters in your Hamiltonian. It's just a single term, so J is effectively your temperature. I might have called J rho S over T at some point when I derived the action, I forget. So, so let me just draw how the flows look. So I have T and Y. I have the Kosterlitz-Sallis transition, pi by 2, J is equal to 1. Okay, so just remember without any fugacity, this is my quasi-long range ordered regime up to 0. And here's my paramagnetic phase. Right, so I have vortices up here, no vortices down here. And if you solve for all the flows, you'll see a flow diagram that looks like this. So it looks like this, and anywhere here flows into here. Because Y, right, from the sign of this, is relevant or irrelevant whether or not you're above or below TKT. So if you're below this line here, then it's always, everything's irrelevant. So everything in this regime, all fugacities in this regime are irrelevant. So that's reassuring. It means that if you introduce some vortices, as this is kind of like what the Monte Carlo simulation did that we looked at. You always have some statistical chance, from the grand canonical Boltzmann, whatever you call it, distribution, of introducing a vortex pair. It's just like locally, right? And it's irrelevant. So even though you can have some sort of finite, fugacity, finite number of vortices here, then you'll still flow to the quasi-long range ordered. But if you start introducing vortices above TKT, then you'll flow to some paramagnetic trivial fixed point way up here. Questions?
So those dots in the diagram, they represent vortices that you've just introduced?
Yeah, I'm just saying it's you're at some temperature, you have some fugacity or some chemical potential, introduce vortices. I mean, just a question of where do these lines, does it mean anything to have, 0 temperature in, finite fugacity? I don't really think so. So imagine that you're here, you're asking what phase are you in, you're flowing to this line. And so remember, it looks like a whole line of critical points in some sense because, it's algebraic everywhere here. Other questions? So I kind of want to derive. So the thing with the Kosterlitz-Sallis transition is there's no signatures in the specific heat. There's no exponents like that. There's no alphas that come from specific heat or susceptibilities. So people didn't see that for a long time. If you just take the XY model or you take some sort of physical system like helium, look at the specific heat in 2 dimensions. You see some sort of peaks, but you don't there's no critical exponent that you can extract to try to see Kosterlitz-Sallis. And there's a reason if you solve these RG equations and look at the free energy that they give you, then you see that it's called an infinite order transition. So you can take an infinite amount of derivatives of the free energy without seeing a singularity. And so there's no singular part to the free energy that gives you this critical behavior that we always assume. And that's why measurements don't reveal Kosterlitz-Sallis very easily. So maybe I want to do that next class. The next class is our last class too. I kind of wanted to do a bit of entanglement scaling. Maybe I'll do both. Maybe I'll do them both real quickly. Entanglement scaling, it's nice. I just want to demonstrate that you can use renormalization group ideas to calculate, useful things in quantum, quantum information theory also. So it's just kind of a demonstration. Okay, I'll figure it out. We'll see what happens Friday. Last class, bring all your assignments.